Hello everyone. In this third video of linear algebra, we're going to talk about one of the most important topics related to a matrix called the determinant. And we're going to see some of the properties, some of the theorem and related topics to determinant. So determinant basically is a scalar value associated with a square matrix. So the first thing we need to have is the matrix has to be what? A square matrix like n by n. And then when we say determinant of matrix, which we show basically matrix inside like the absolute value sign, it is going to be a scalar, okay? So it is determinant is an operation that when applied to a square matrix will produce a scalar. Now, what does this scalar say about the matrix? A bunch of things, okay? Like what? So for a square matrix, you can show that the determinant is acting basically very similar to the rank. So when the matrix has basically, if an n by n matrix has n linearly independent rows or columns, we say that it is full rank. The rank of it is equal to n. You can similarly show that the determinant of that matrix is basically not equal to 0. And when it is not full rank, when the rank is less than a minimum number of rows and columns, in this case, since they are the same, is less than n, then you can show that the matrix A is what? It has a 0 determinant, correct? So let me write it for you here. If or let's say rank of A, correct? If A is rank deficient, if rank of A is less than n for an n by n matrix, then we can show that the determinant of the matrix is equal to 0, so we call it a singular or rank deficient matrix. And if it's equal to n, correct? If this rank of A is equal to n, then we can see that the determinant is not equal to 0. Okay, so you see, being 0 or non-zero in determinant is identical to having full rank or not full rank for a square matrix in general. So they are showing whether you have enough or n linearly independent rows or columns or not for the matrix. And then, of course, later when we're going to go and talk about the inverse of a matrix for a square matrix, then we can see that this determinant plays the important role. So if the determinant is 0, you cannot find the inverse. If it's not equal to 0, then you can't find the inverse. So basically, a matrix that has a non-zero determinant, we say it's invertible. The one that is singular is not invertible, okay? And we'll see that in the next lecture when we talk about inverse of square matrices. Okay, so it's a very important thing, determinant. And then depending on how close the determinant is to 0, then we can define other things like condition number and so on, which we'll talk about them later. But it's very important to know that the notion of determinants is a scalar, and it tells us lots of things about the square matrix. Good. Now, some important properties of this determinant operation is if you transpose the matrix, the determinant is going to stay the same. So swapping rows and columns is not going to do anything. If you have two matrices multiplied together, the determinant of the product is the same as the product of the determinants. Okay? Now, that's not the case for addition and subtraction. So determinant of A plus B is definitely not equal to determinant A plus determinant B. Okay? That's not the case. So it's not really a linear operator. It's when you multiply matrices, you can separate them, okay, but not when you add them. And if you multiply each entry in the matrix by a constant c, then the determinant of the matrix is multiplied by c to the n, where n is the number of rows or columns of the square matrix, okay? So these are some important properties of the determinant, and we have a few more. What are they? Well, first of all, What about triangular or diagonal matrices? So if you have a triangular or diagonal, diagonals are a form of triangular, upper or lower, and you have numbers like, let's say, lambda 1, lambda 2, all the way to lambda n on the main diagonal. Here you have some non-zero numbers, and here you have a bunch of zeros. So let's say it's upper triangular. When you calculate the determinant of such matrix, the determinant of that is going to be simply the product of the elements on the main diagonal. So it is going to be lambda 1, lambda 2, all the way to lambda n. Okay, and of course, when it's diagonal, that's the same thing, because diagonal is a triangular matrix. And if you have a matrix that is what we call a block matrix, so you have a matrix A, which itself is composed of basically augmenting several other matrices, like you have B, you have C, you have D, and 0, right? Maybe I can write it as 0, C, and D to make it more similar to an upper triangular or lower triangular. So you see this here, this A is composed of these matrices B, C, D. So let's say, for example, this is a 6 by 6, and so these matrices are like 3 by 3 each. Okay, so it's not like these B, C, Ds are numbers, no, and 0 matrix, they are all submatrices. If I say what is the determinant of A, the large matrix, you can say it's equal to determinant of B times determinant of C. The product of determinants of the diagonal entries. Okay, so this is for a block matrix, and I'll show you. So these are all separate cases. Then, for example, what's determinant of an identity matrix? I n by n. Well, all the diagonal elements are 1, everywhere else is 0, so clearly determinant of identity matrix is equal to what? Equal to 1. And since it's not equal to 0, means the identity matrix can be inverted. What is inverse of it? Again, we'll see in the next lecture. That's the I itself. So these are some important properties of this determinant operator. But so far, we have not talked about how to calculate it. We introduced that this is an operator that gives you a scalar for any matrix, but we haven't talked about the most important thing. How would you calculate this determinant? So there are different ways to do it. One of the most famous ones is called the expansion method, or Laplace expansion method, which works for basically any type of matrix, okay, regardless of the dimension of it. And the expansion method says this. It says the determinant of a matrix A, which is like A11, A12, all the way to A1n, A21, all the way to AN1, right? And then go all the way to ANN. Okay, so it says the determinant of this n by n matrix is what? You choose any row or any column as you wish, and then you expand about that row or that column. Let's say, for example, if we choose the first row, how do we determine or calculate the determinant? It says, well, it is equal to the first element, A11, times -1 to the sum of these two subscripts, 1 plus 1, times determinant of a matrix that has the first row and the first column eliminated. We call it minor 1, 1. Okay, and then plus A12, the second element, times -1 to the power of, again, these two subscripts added together, and determinant of a matrix where the first row and the second column of the matrix are eliminated. We call it minor M12, and keep all the way to what? A1n times -1 to the 1 plus n, determinant of a matrix where the first column and the first row and the nth column are eliminated. Okay, so this is called here expansion with respect to the first row, right? And what does it mean? So let me first write it for you. So this is called, for example, expansion with respect to the first row. Can I expand it with respect to other rows or other columns? Yes, I'll show you all of them. And all of them will give you the same number, so it does not really matter which one to use. But if you want to have some preference, I'll tell you which one is better to expand. So there are n rows and n columns, so in general there are 2n ways, 2 times n ways to expand this, right? So this was like the first column, right? Now first row, let's say for example now third column. So third column means what? Means the element is what? Or let's say second column, since you can see it. So the second column is this, correct? The element is A12, A22 all the way to AN2. So if I want to expand with respect to this second column, I multiply the first entry, A12, times -1, again to the power of the two subscripts added together, 1 plus 2, times determinant of a matrix that has the first row and the second column eliminated, minor M12, and then we keep doing that, okay? We keep forwarding by multiplying each element by -1 to either an odd power or an even power and multiplying by a minor. And keep going all the way to the last element of that column. Okay, so what is this? This is expansion with respect to the second column. So as I said, you can expand with respect to any column, any row, and the result of them are going to be the same. I'll show you. Okay, it doesn't matter which row or which column you use for expansion, the result is always going to be the same. That's the beauty of the definition of determinant in this Laplace expansion. So now we have some terminologies, and the terminologies are minors and cofactors, and then later on adjudicate matrix. Okay, or maybe we can keep the adjudicate matrix for when we talk about the inverse, because that is more useful when we talk about inverse. So let's keep the adjudicate and cofactor matrix later, but the idea of cofactor and minor, it is important to talk about them right now. So I mentioned the minor for you, this M11, M22, and so on. This guy here, each one of these elements is called a minor. So minor is not a submatrix, because M11 means the same as A, except the first row and the first column eliminated, okay? So what does M11 mean? Means, again, take the first row and the first column out. So you're going to get a smaller matrix, this guy here. And this matrix is going to be n minus 1 times n minus 1. And the determinant of this n minus 1 by n minus 1 submatrix, this whole determinant, not just the submatrix, the determinant of it is single number. This is what we call a minor. Okay, so minor is the determinant of a submatrix. And by submatrix, we mean a square matrix that has basically a row and a column eliminated. Okay, so these are all called minors, right? Now, what is cofactor? Cofactor is when you multiply them by that -1 to the sum of the subscripts. So if somebody says, what is the, let's say, minor in here, you say this term, this whole thing here, here, here. These guys are what? These guys are, you might call cofactor. So if I want to write them down somewhere for you, these guys are called cofactor. Okay, so you might show them with Cij, cofactor ij, which is basically -1 to the ij, I plus j, times determinant of the submatrix Mij. Okay, so this is called cofactor. And we'll see the matrix formed by all these cofactors we call cofactor matrix, and the transpose of that we call the adjacent matrix. But we'll talk about that in the next lecture when we talk about the inverse matrix. Okay, so for now, let's keep that in mind, the meaning of minor, submatrix, and cofactor. And now it is a good time to practice with this. Okay, let's practice with this. And to make life easy, we first start by a 2x2 matrix, which is the simplest. So the determinant of a 2x2 matrix with entries A, B, C, D is equal to what? So let's use the first row and expand, right? So it is going to be element 1, 1, which is A times -1 to the 1 plus 1. And the determinant of the matrix that has the first row and the first column eliminated. Right? So if you eliminate first row and first column, all you have is D. So basically this whole thing is going to be the determinant of D. And then plus, now the second element, which is B, so it's going to be B times -1 to the 1 plus 2 times, now what? A matrix where the first row and the second column are eliminated. Basically the row and the column that has this B at its intersection, right? So if you write it as determinant of a submatrix M12 or minor M12, this here is simply going to be determinant of C. And for a scalar, determinant of a scalar is equal to the scalar itself, of course. Okay, it's like the scalar itself, right? So what do we get? This is going to be +1. This is D, so it's going to be A times D, and then this is -1 here. So there's going to be -B times C. Okay, and again, please pay attention. Determinant of the scalar is the scalar, not the absolute value of the scalar. Okay, so determinant of a scalar, let me write it this way. Determinant of a scalar is equal to the scalar, but determinant of the scalar is not equal to absolute value of the scalar. So although the symbol we chose for determinant looks like the absolute value, but when we plug in a scalar in it, if it's -2, the result is -2, not +2, okay? So please keep that in mind. And here we go. So the result for the determinant of a 2x2 matrix is AD minus BC. Now, what is AD minus BC? Well, if you look, it is what? It is the product of the elements on the main diagonal minus the products of the elements on the anti-diagonal or the non-major diagonal, correct? So the product of the elements on the main diagonal minus the product of the elements on the anti-diagonal. Now you might say, what if you expanded it with respect to another row or another column, right? So let's do it with respect to, let's say, second column here. So we go here. If we do that, what do we get? It's going to be the first element b times -1 to the row and column index of that entry, because remember, this is 1 and 2. B is the matrix 1 and 2, so it's going to be 1 plus 2 times determinant of a matrix that results from eliminating the row and the column that share B, which is this one and this one, correct? So you might call that M12, that submatrix, and so clearly that is going to be determinant of C, right? And then plus, now the next element, which is D times -1 to the 2 plus 2, because that's element 2, 2, determinant of a matrix that has second row and second column eliminated. And if you do that, that means A, correct? So if we do it, what do we get? Again, this is -1, this is +1, so it is going to be -BC plus what? D times A. And you see this one and this one are the same thing. And if you did it with respect to first column or second row or any of that, the result is not going to be any different. So it doesn't matter with respect to which row or which column, the result is always the same. Okay, so that's a 2 by 2. Now let's practice on a 3 by 3 as well. So let's say I have a general 3 by 3. And if you want, I can write it as A, B, C, D, E, F, G, H, and I, J, K. Let's use K. So what is it? So here I'm going to expand, let's say, with respect to the first row. So there's going to be A times -1 to the 1 plus 1, determinant of M11, plus B times -1 to the 1 plus 2, determinant of M12, and finally plus C times -1 to the 1 plus 3, determinant of M13. Now, what is M11? M11 means eliminate first row and first column. So M11 is EFHK. So if I write it, this is the determinant of E, F, H, and K. This guy here means eliminate the first row and the second column. So the result is going to be DGFK. And finally, this one means the first row and the third column. So you have to do this one, and so you get DEGH. Right? And these negative numbers, this is 1, this is -1, and this is +1. So if you expand it, and you know now these are 2 by 2, so calculating the determinant means product of diagonal minus anti-diagonal. So this is going to be A times EK minus FH minus B times DK minus FG, and finally plus C times DH minus E times G. Correct? So if I expand it all, it's going to be AEK, let's add all the positive numbers together, plus BFG, and then plus CDH, minus, you will get AFH, and then BDK, and then CEG. Okay, so if you look, you clearly see 3 terms are positive, 3 terms are negative. Okay, so this is how you can go about calculating a 3 by 3 by expanding. And again, it doesn't matter which row or which column. Now, there is an equivalent method of doing it for a 3 by 3. If you have a 3 by 3 matrix and you want to calculate determinant, there is a faster, more interesting way developed by a person named Sarus. So when we say the Sarus's law, basically, well, let me go here. Sarus's law, Sarus's rule, actually, not law. What do we mean? By the way, here I'm thinking more this characteristic polynomial. I can say it right here, but and Cayley-Hamilton Theorem. I can say them here, and or I can talk about them when I talk about eigenvalues. But you know what? I'll tell you about them here. So that's okay. So if I go back now, what is the Sarus's method? So the Sarus's method says this. Says one way to calculate the determinant of a 3 by 3, and this is only valid for a 3 by 3. You cannot apply it for a 4 by 4 or anything. The Sarus's method is only available for a 3 by 3. Okay, so let me write it for you here. Sarus's law, or a rule, not law, maybe it's better to call it Sarus's rule, which is only for 3 by 3 matrices, but many of the matrices we deal with in mechanics, in robotics and so on, they're mostly 3 by 3 because we are living in a 3D world, Euclidean space, and so when we do cross products and so many other things, these 3 by 3 matrices are quite common. So the way that Sarus says you can do it is this. He says you copy the first 2 columns and put them on the right side. You see here, so I'm copying them and then adding them here on the right hand side, just like this. That's all you need. Now, what should you do? He says multiply the 3 elements on the main diagonal of what? The original matrix. What would you get? You will get AEK, correct? Then what? Shift your diagonal 1 unit to the right. If you do, you will get to this new one. So it's going to be what? Plus BFG. And it says shift it 1 more time. What is it? Plus CDH, right? So the main diagonal and the 2 parallels to it are multiplied all elements together. That's positive. Now minus what? So last time we did the main diagonal and the 2 parallels. This time we do the anti-diagonal. What's the anti-diagonal? That is CEG. Again, shifted 1 unit to the right, AFH, and shifted 1 more unit to the right, you get what? BDK. And that's it. And now if you compare side by side, the top one and the bottom one, these two, you'll see that they are equal. Okay, so you can get it by expansion and calculating all the cofactors and everything. Or you can just copy the first 2 columns, the 2 diagonal and the parallels to it are positive, the anti-diagonal and parallels to it are negative, and this one gives you a lot faster solution than that one does. Okay, so the Sarus's method, the Sarus's rule is very, very good, very useful. I always use it in my classes and teach it to my students. But again, it is only for a 3 by 3. Once you have a 4 by 4, you cannot use it. Of course, for a 4 by 4, you can expand it. And then since the minors are going to be 3 by 3 for those 3 by 3, now you can use the Sarus's method. Okay, so just keep that in mind, the limitation of the Sarus's rule or method. Okay, so that's a determinant. Now, I mentioned something. It's good to talk about it right now. So I told you about the expansion. You can expand with any row or any column. But is there any preference? The preference is if your matrix has some zeros in a row or column, you go for that row or column. So let's say you have 3, 5, 0, 6, let's say 9, 0, and let's say here 1, 2, and 4, right? So here, although I can choose anything I want, but I definitely choose the third column because it has 2 zeros. So I do not need to even calculate their cofactors and multiply by 0 and 0. It's going to go away. So all I need here is 4 times -1 to the sum of the row and column location, 3 and 3, and the determinant of a matrix that has row 3 and column 3 eliminated. So that's 3, 5, 6, and 9, and this is going to be 27, correct, minus 30, the product of diagonal minus anti-diagonal, so that's -3. This is 1, and that is going to be -12. Done. Okay, so I'm definitely not interested in expanding with respect to first row, column, second column, or third row. Even if you did first row or second row, at least one of them is 0. But definitely the answer is the row or the column with the maximum number of zeros. That is where you expand to make it as fast as possible. Okay, so please keep that in mind. Okay, so this is about determinant of a matrix, how to calculate it using the Laplace expansion, how to do it using the Sarus's rule. There are other methods in the literature for calculating the determinant of a matrix, but I guess one of them, knowing that, is enough. And in MATLAB, the command to use is determinant, okay, DET. So if I have any matrix, let's say A is equal to a random matrix of 6 by 6. So 6 rows and 6 columns, all random numbers between 0 and 1. Drawn from a uniform distribution of numbers, and then all I need is to calculate determinant of A, right? So here we go. You see the determinant is non-zero, close of course, because you're getting it from a bunch of random numbers, but definitely non-zero, so the matrix is not really singular. Okay, so that's all you need, DET in MATLAB. Finally, as I said, we need to talk about the characteristic polynomial and the Cayley-Hamilton theorem. So first of all, what is characteristic polynomial? The characteristic polynomial of a matrix n by n is this. It's written like lambda n plus c1, lambda n minus 1, and so on. But if you really want to write it, it is going to be the determinant of what? It's going to be the determinant of the parameter lambda or any other parameter. It doesn't need to necessarily be called lambda. The reason we do it is because later we use it for eigenvalues, okay? But again, you don't really have to, in this case, to call it that. And so all it is determinant of lambda times identity matrix n by n, which is the same size as A, minus A, and set it equal to what? Set it equal to 0. Okay, so this thing here is the characteristic polynomial, right? This one. So that's the characteristic polynomial. Why is it called characteristic polynomial? We'll see when we get to the eigenvalues, because it will give you the eigenvalues. The solution to this polynomial of nth order equal to 0, the solution for the lambdas are called the eigenvalue of a matrix, and the word eigen is a German word, means characteristic. So this is a polynomial that gives you the characteristic values or eigenvalues, okay? So what you need is you multiply the identity matrix by lambda. So the result of this is a diagonal matrix where all of the entries, instead of 1, they're all lambda. Subtract it from A, calculate the determinant, set it equal to what? 0. So for example, if I have a 2 by 2 matrix, let's say A is equal to 3, 5, 1, and 4, right? What is the characteristic polynomial? So you need to first form the matrix lambda I, and I is the same dimension as A. So if this is 2 by 2, that is going to be a 2 by 2 minus A. So it's going to be what? It's going to be lambda times 1, 0, 0, 1 minus A, which is 3, 5, 1, and 4. And as you know, when you multiply a number by a matrix, each and every one of the entries is multiplied by that. So the result of this is simply going to be lambda 0, 0, lambda. And when you subtract two matrices with similar dimensions, you subtract corresponding elements. So you get lambda minus 3 as element 1, 1, negative 5 as element 1, 2. Then you get negative 1 as element 2, 1. And then you get lambda minus 4 at element what? 2, 2. So now when I say what's the characteristic polynomial p lambda of A, that means setting the determinant of that matrix to what? To 0. And since this is a 2 by 2 matrix, it's going to be the product of the diagonals, which is lambda minus 3 times lambda minus 4. Then minus the product of the anti-diagonals, which is negative 1 and negative 5, and set that equal to what? 0. Okay, so this is the characteristic polynomial, and if you simplify it here, you will get lambda squared minus 7 lambda. That's 12, that is 5, so it's going to be plus 7 is equal to 0, right? So this is the characteristic polynomial of this matrix. It has two roots. The roots of it we call the eigen values of matrix. Again, what are they? We are going to talk about it in a couple of videos from now. Next lecture, we're going to talk about inverse and pseudo-inverse. The one after that, we talk about eigenvalues and singular values. But right now, just take it from me that this is how we form this characteristic polynomial. And now the Cayley-Hamilton Theorem says, if you plug the matrix A itself into the characteristic polynomial, so if you plug in actually P of A, not P of lambda, if you plug in A instead of lambda in the characteristic polynomial, the result is going to be what? It's going to be 0 again, with one difference. This 0 is not just number 0. It is a 0 what? N by n, the same dimension as the matrix, okay? So it's not like it is going to be number, because these are all matrices. And the Cn, by the way, needs to be multiplied by the identity matrix, right? So it can be added or subtracted from the rest. So that's what Cayley-Hamilton says. Plug in the A matrix into its characteristic equation. The result is going to be still valid. What does it mean for us? It means here, if instead of lambda I plug in A, what do I get? I will get A squared minus 7A, and then plus 7. Now the 7 has to be multiplied by the identity matrix 2 by 2. What's the result of this? Well, let's do it just for the sake of practice. So A itself is 3, 5, 1, 4. So when we square it, means you multiply it by itself. And then minus 7 times this. So 7 should be multiplied by each and every one of the entries. And then plus 7 times the identity matrix, 1, 0, 0, 1. Right? So this is the result. And here, if we carry out the matrix multiplication, you get a 3, a 9, and a 5, so you get 14. Then I go over next one, that's 15 and 20, that's 35. That's a 3 and a 4, that's 7. That's a 5 and a 16, that's 21. Minus 7 is multiplied by each and every one of the elements, and then here again 7 is multiplied by each and every one of the elements. And now what do we get when you add them together? So you will get 14 minus 21 plus 7, clearly 0. You get 35 minus 35 plus 0, again you get 0. You get 7 minus 7 plus 0 is 0. and you will get 21 minus 28 and then plus 7, which again is what? 0. You see? So when I plug matrix A into its own characteristic polynomial, the result is a 0 matrix of the same size as A is. Good? Now you might say, okay, fine, good. We found that it is. Now, what's the point? How can I use it? Well, the use is this. If I know this, then I can, instead of me calculating a to the power 2, since this is equal, this whole thing is equal to 0, 2 by 2, right? Here, a squared minus 7a plus 7 times identity matrix is equal to 0. Then if I want a squared, I can take these other terms to the right-hand side. It's going to be 7 times a minus 7 times I. So anytime I want to calculate the A matrix to the power 2, what do? I will calculate 7a minus I for it instead. And you might say, okay, fine. Still, what's the point? Well, now I'll tell you the point. So let's say here you want to calculate, for example, the exponential of A. Remember in the first lecture we talked about functions of matrices, right? So if I want to calculate exponential of A, how do I do that? Well, if you remember, we said it's not like raising the Euler number to each and every one of the entries in A, right? What you need to do for this is to use what? To use the Maclaurin series. So it's going to be I plus A plus 1/2 A squared plus 1 over 3 factorial A cubed and all the way going, right? So now this I is clearly a 2 by 2, fine. This is a 2 by 2, fine. Instead of A squared, I'm going to plug in what? 7a minus 7I. What about A cubed? Well, you say A cubed is what? Is A squared times A. But what is A squared? Itself is 7a minus 7I. Multiplied by A, you will get 7a squared, and then what? Minus 7a, right? Because I times A is the same as A. Remember, I is acting like number 1. And again, you can do another simplification. Now that A squared is 7a minus 7I, plug it back again one more time. So it's going to be 7 times what? 7a minus 7I, then minus 7a, right? And you'll get what? This is going to be 49a minus 49i. So the result is going to be 49 minus 7. It's going to be 42a minus 49i. So you see, anytime that I have a cubed, I can also write it as a simple number times a plus a simple number times identity. And similarly, I can show you that any other power of a, 2 or bigger than 2, can ultimately be written as what? A single number times a and plus a single number times I. So in general, this whole thing, even when you keep doing it, this whole thing, when you do it at the end of the day, is going to be a simple number a times a plus what? Another number times I. And the thing is, if you look at the weights of these terms, they are really reducing. And when you add those single coefficients of a in them, like this 7, this 43, and so on and so forth, 42, they ultimately will converge to a number because the magnitude of them is reduced. If you look, this factorial is basically growing very fast. If you look, for example, at the weight of I, it is 7 squared, right? Which is this number squared. So if you go to the a to the 4, you probably expect something like 7 to the 3 to appear behind I, right? And go to a to the 5, it's going to be 7 to the 4. So what you have here is a power function like n to the a, right? But they are all divided by n factorial. And you know that n factorial for n gets bigger and bigger is always growing faster than the power function. So ultimately, these terms, contribution of them will get to 0, and you really can write the whole thing as a single number times the A matrix plus another single number times what? Times the identity matrix, as long as the matrix is what? 2 by 2. Now, what if the matrix A is 3 by 3? When it's 3 by 3, you can, based on Cayley-Hamilton, you can write A cubed as a function of smaller powers of A. So C1 times A squared plus C2 times A plus C3 times I, where I is 3 by 3. And not only that, you can also write in general, not only power 3, you can write any power of A as long as that power is bigger than or equal 3. You can write it this way, like C1A squared plus C2A plus C3I 3 by 3. And so when you have a function of A, you can also write it this way as well. Okay, so in the distribution of in the calculation of functions of a matrix, the Cayley-Hamilton theorem can be extremely useful because you really do not need to keep multiplying a matrix n times by itself. It says if it's n by n, if it's 3 by 3, the maximum power that you need for any function is power what? 2 of that matrix. Right? Because any power 3 and above can be written as a combination of power 2, 1, and identity. Okay, so this is extremely useful, right? If you remember, again, I told you in the first lecture about functions of matrices, and I showed you how to go about calculating that, right? So here, when you have like a matrix A, and this matrix A is like a 3 by 3 matrix, 3, 2, 5, 0, 9, 8, and then 6, negative 1, and 2. And then we say, what is exponential of A? It's not really raising each Euler number to each and every one of those entries, right? It is using the Cayley-Hamilton theorem to show you that this is exponential of A. Okay? And the numbers, if you can see, they are like 27, 148, and so on. The biggest number that you get is about 8,000. Okay, but definitely this is different than, as I said, raising e to each and every one of the numbers in A. Okay, so that's how the Cayley-Hamilton theorem is used. Well, I think before we finish the lecture, it's worth talking about another application of determinants, and that is the Cramer's rule, where we use the determinant of matrices to solve a system of linear equations. So this Cramer's rule says if you have a linear system of equations ax equal to b, where the unknowns are x1, x2 all the way to xn, so your coefficient matrix is n by n, your unknown vector is n by 1, and your right-hand side known values are n by 1, then each one of the unknowns, xi, can be found by determinant of a matrix called ai divided by the determinant of the coefficient matrix A, where what is ai? Ai is the same as A, where the ith column in A is replaced by the right-hand side B. Okay, so what does that mean? Let's say, for example, I have a system of equations like 2x minus 3y is equal to 1 and negative 4y plus x is equal to 6. Okay, so what I will do, I will rearrange it into the matrix format. So this is going to be 2 and negative 3, and here if you rearrange it and write it as x minus 4y, It's going to be 1 and negative 4. This whole thing times x and y is equal to 1 and 6. Okay, so this is your A, this is your unknown vector x, or you might call it z, or whatever you want, and this is the right-hand side B. So now it says each one of the components in the unknown z1, which is x, is equal to determinant of a 2 by 2 matrix divided by A. So A is 2, negative 3, 1, and negative 4. And here, since x is your first element in Z, you replace the first column of A by the right-hand side. So basically, you bring this 1 and 6 and put it in place of 2 and negative 1. So you get 1 and 6, and the rest of it is negative 3 and negative 4. So the first column, again, in A, I replaced it by B. That gives me the first unknown entity, and here that's not hard to calculate, right? That's negative 4, that is plus 18, so that's 14, and this is negative 8 plus 3, that's negative 5. So the first answer is negative 14 over 5, and then it says y if you want it. Very similar, it is a determinant of A2 divided by A, where A2 is the same as A, except the second column of A is to be replaced by the right-hand side. So this is A, keep the first column, but the second column of A is to be replaced by what? By B. So that is A2 basically. This is going to be A1. So A2 is going to be 1 and 6 here. And again, if you calculate this, it is going to be 12 minus 1, so that's 11. And this is going to be 8, well, let's see, negative, oh, that's a negative 4. Negative 8 plus, that's negative 5. Okay, so one of them is negative 14 over 5, the other one is negative 11 over 5, and that's it. Solution is done. And this Cramer's rule, you can prove it, but again, here in this video, we are not after proving anything. We are learning tools, and we are learning how to properly use the tools and their details, but not the proof of them. If you want, you can always refer to a text in linear algebra and see the proof for the Cramer's rule. But it is a very nice solution to a linear system of equations. The problem is, since it needs calculating two determinants and dividing, when the size of the unknowns and the coefficient matrix right-hand side gets larger, the computation of it is quite more than what we did, if you remember, in the first lecture when I showed you how to use the, or actually the second lecture where I showed you how to solve a system of equations using Gaussian elimination method, right? When I showed you how to use Gaussian elimination or Gauss-Jordan elimination to solve a set of equations, that in general requires a lot less computation compared to the Cramer's method. For a 2 by 2, 3 by 3, this method is amazing because you can easily calculate the determinant of a 2 by 2 or 3 by 3 on the paper. 2 by 2 is easy, diagonal minus anti-diagonal products, and 3 by 3 we use the Sarus's rule that I told you in this lecture. But once you go further to higher dimensions, 4, 5, 6, 10, 100, and so on, then calculating these determinants is going to be quite costly operation compared to simple row operations and converting your left-hand side into an upper diagonal or a upper triangular or a diagonal. So just wanted to tell you another application of determinants. Well, thank you so much for paying attention to this lecture, and I will see you in the next video. Thanks.